In this video, we're going to look at polyprotic weak acids. So these are weak acids with more than a single H plus that could be released. So carbonic acid. Well, the first H plus released will create a bicarbonate. However, that bicarbonate has an H plus that could also be released. So we really have two possible reactions. We can lose our first proton, and then our bicarbonate ion can lose a second proton to form carbonate. When you have polyprotic acids, there's actually a Ka for each of the steps. So there's Ka1 and there's Ka2. For bicarbonate, 4.5 times 10 to the minus 7 and 4.7 times 10 to the minus 11. It is easier to lose the first proton than it is to lose the second. Our first proton is leaving a neutral molecule, but our second H plus is leaving an anion. That negative charge attracts the positive, it makes it harder to leave. These are significantly different enough that we generally perceive this as stepwise reactions. We really will lose one proton, and then the conjugate base formed may eventually lose a second proton. But they are done independent. This modifies how we have to go calculate out the amount of H plus that this weak acid would generate. If we have a second step that can make some extra H plus, how do we factor that in with our equilibrium? Conveniently, we usually are only concerned with the first step. If we think about how significantly different these Kas are, the first step is going to be much larger at making product than our second step. And so the extra H plus generated by the second step is going to be pretty small compared to the H plus generated by the first step. Let's look at that in a little deeper. So let's find the pH of 0.050 molar H2CO3 solution. I'm going to have my carbonic acid. It's in equilibrium with H plus and bicarbonate. There's going to be some initial values, 0.050, and start with none of the other materials. We're just putting in the weak acid. There's going to be some change. We're going to lose some weak acid. We're going to gain some products. And we'll eventually reach equilibrium. Given how small Ka1 is, it's safe to assume that we can probably simplify this and just say that indeed we do lose a little bit of our starting material, but within our air, it's just going to round back to look like the starting value. So we can save ourselves having to do the quadratic equation. Plug this in, our Ka, 4.5 times 10 to the minus 7 is going to equal X for H plus, X for our bicarbonate, and the simplified 0.050 for our acid. Multiply it up, square root it, our X value is going to be 1.5 times 10 to the minus 4, which if I wanted to find the pH of that, negative log of 1.5 times 10 to the minus 4 is going to be 3.824. So if we put just the weak acid in its fully protonated form into water, we expect this first step to happen and to free up 1.5 times 10 to the minus 4 H plus. Well, then let's think about our second step. Simply put, we can imagine our second step has HCO3 reacting to give away H plus and carbonate. This had a Ka, our second Ka, of 4.7 times 10 to the minus 11. This time, however, our initial, well, they came from the first step. So we know our bicarbonate from before. It was X. There's 1.5 times 10 to the minus 4 bicarbonate. There's actually 1.5 times 10 to the minus 4 H plus, and at the moment, no carbonate. The second step hasn't occurred yet. Well, there's going to be a change. I can't do the reverse. I still don't have any carbonate, so I'm going to lose a little bicarbonate. That means I'm going to make a little H plus. I'm going to make a little carbonate. I'm going to reach equilibrium. Our calculation becomes a little bit more complex if we try to put it in, but still 4.7 times 10 to the minus 11 has to equal our H plus. 1.5 times 10 to the minus 4 plus x, all divided by 1.5 times 10 to the minus 4 minus x. Well, can we do any simplifying assumptions here? We have some pretty small concentrations, but look at our Ka here. We want it to be really tiny. And, well, part of our top is almost the same size as part of our bottom. So the only way to get the top smaller is if x is really, really small, so that when I multiply it versus this other number, it ends up making the top really tiny. I need it to shrink a lot if I want to get down to 10 to the minus 11. So x must be excruciatingly small here to pull this off. So yeah, we can fairly safely assume that the change by x is going to be really small versus the starting amounts that are there. Well, the net effect is, that means our bicarbonate and our H plus concentrations, which came in the same, despite technically changing a little, are going to change so small that they basically just cancel each other out in the calculation. You have the same on top and bottom, they cancel out, and really our bicarbonate concentration just looks like 4.7 times 10 to the minus 11. Just the tiniest bit of our bicarbonate will actually separate into H plus and carbonate. Way less than the 10 to the minus 4 that we already had going on. As a result, the second step contributes effectively 0 H plus. I mean, yes, there is technically a little bit, but that's way below the 2 decimal places we have in our value up here. When you have a polyprotic weak acid, it is really only the first step that determines the pH. The second or even third are generally not strong enough to alter the pH. They will be orders of magnitude less H plus generated by the later steps than the first step. And as a result, simply won't be able to alter the molarity by any noticeable amount.